there is benzylic radical halogenation. That is, the benzylic CH bond is unusually weak, and therefore when you expose an alkyl benzene, and here I'm just doing it for methylbenzene, common name toluene, to a halogen under conditions that generate a radical, that is bromine with heat or light or a peroxide, a radical initiator, so you get Br dot, a very rapid radical chain reaction will set in where the benzylic position is brominated, and you get the corresponding bromomethylbenzene. Notice that the bromine does not attack the benzene ring to give you ortho power substitution, because under these conditions, the Br dot is much, much faster in pulling off this proton than Br plus adding to the benzene ring. Moreover, with bromine in this particular setup, nothing will happen anyway because you need a Lewis acid to activate for electrophilic aromatic substitution. Okay? But even in cases where you have an activated benzene ring, alkoxy substitute and so forth, if you generate the Br dot, the radical halogenation takes over. It is so much faster than the regular electrophilic aromatic substitution, it doesn't come into play. And this is completely analogous to the allylic halogenation of a double bond, where the radical process gets the bromine to go for the allylic carbon as opposed to doing an addition to the double bond. Remember, we discussed that. The addition to the double bond still goes on at its regular rate, but that rate relative to the radical reaction is so much smaller that it doesn't enter into the picture in terms of product distribution. So you get benzylic bromination. Chlorination, for example, you do need light. Heat is not enough because the chlorine-chlorine bond is stronger. So typically you use light to induce the chlorine-chlorine bond to break, and you get chlorine dot, and the chlorine dot then attacks at the benzylic position. And notice for this particular system, since you have 3 hydrogens, you can displace them in a stepwise manner and get monochloro, dichloro, trichloro, and so forth. So mechanistically, this is completely analogous to the allylic halogenation, except now we're doing it for the benzylic halogenation. So this is the weak bond. You generate X dot by hook or crook, either heat or light or radical initiator, like a peroxide. And as soon as you get, essentially, in theory, only one X dot, it will turn over in these 2 propagation steps. So the X dot attacks the H, rips it off, you get the benzylic radical, and that radical attacks X2 to make the product plus a new X dot. That X dot goes back here. And so you can see that in principle, one X dot could turn all of starting material forward to product. This, again, completely identical mechanism to the allylic radical halogenation. So if you imagine wiping off this butadiene portion 3 times, that's exactly what we did in chapter 14 I think it was my first lecture, in fact. So why is this a weak bond? Because the benzylic radical is stabilized by resonance, and this you can in principle view as sort of like a super allylic resonance, but we call it benzylic because it involves the entire benzene ring. So if you just focus on the first double bond, that's allylic resonance that puts the dot here, that's this one, and then another allylic transposition puts the dot here, and again puts it here, and that shows you that the dot is really delocalized over the entire benzylic system. And so the molecular orbital picture, or atomic orbital picture, looks like this, which is essentially a replica of the model I just showed you, and the electrostatic potential map shows you that it's sort of yellowish green all over on all the carbons, indicating that the electron density is smeared out over all 7 carbons. Now, there's one beautiful aspect of benzylic halogenation, which is actually an advantage over allylic halogenation, and that is regioselectivity. Notice that if you think of this as an allylic system, in principle, this is an unsymmetrical double bond. Okay? Or to put it differently, when you look at the intermediate here, attack, I've written the attack of this dot on X to put the X here, but in principle, since we have all these resonance structures, attack could occur also here, and of course here, which is by symmetry the same as here. So in principle, you could get a mixture of isomers. That's exactly what we saw for unsymmetrical alkenes, right? Where attack could occur on the 2 sides of the allylic radical system, and if the 2 sides were different, because they had different substituents, then you would get a mixture. Okay? So that was a drawback, in fact, of the allylic halogenation. This doesn't happen here, and the reason it doesn't happen is obvious. Attack at the ring will destroy the aromaticity. So it doesn't want that. So it only goes to this position here. And that makes it a simpler reaction, actually, than the allylic halogenation. Okay, so radical halogenation goes benzylic. That's relatively easy. Okay? So can we look at leaving group ability of a benzylic leaving group? So here I have a toluene sulfonate or methylbenzene sulfonate, our very good leaving group that we've mentioned several times. You could use a bromide or chloride as a leaving group. Just pick that one in order to remind you of this being an excellent leaving group. And indeed, this, if you let it sit in the absence of a good nucleophile in a proteic solvent like water or ethanol, it will undergo an SN1 reaction. That is, the leaving group will leave and give you the benzylic cation, and that will then be trapped by the ethanol. Interestingly, you need a little bit of a kick. The parent system, without the methoxy, in other words, benzyl itself, phenyl methyl itself, is too slow to undergo an SN1. It just the benzylic cation is just not stable enough, interestingly. But with methoxy, you can observe that very nicely, and you get the SN1 reaction. And so how does this go? Well, the leaving group leaves, and you get a resonance-stabilized benzylic cation. And you can see what happens. The benzene ring is involved by donating electron density, so this plus charge moves over here. So this is the allylic cation resonance. Here's the second one that puts the plus charge here. And then there's a really good one where you donate this electron pair towards the electron sextet on this carbon, and that gives you an octet. This all looks, we've done that before in electrophilic aromatic substitution. It all should be really an easy one for you to reproduce. Okay? And so then this guy is trapped by the ethanol to give the product. SN1 is relatively good, as in allylic systems. SN2 is also accelerated, and it's accelerated for the same reasons. Okay? So if you react this with cyanide, typically good nucleophile, under typical SN2 conditions, which is some polar solvent, protein or not, you displace the leaving group. So here I'm using bromide as a leaving group. That gives you the corresponding nitrile, phenyl ethane nitrile. This goes about 100 times faster than the SN2 reaction of typical primary bromoalkene. And the reason that this is faster is because this guy is not a typical alkyl group. It involves a carbon attached to this reacting carbon, electrophilic carbon, that's sp2 hybridized as opposed to sp3. More S character, electron withdrawing. So that makes this carbon more blue than the corresponding carbon where this carbon would be, say, methyl. Okay? So more reactive. Cyanide will attack it faster. A second reason is, again, very analogous to allylic SN2, is that the SN2 reaction, remember, involves inversion at the reacting center. The nucleophile comes in, the leaving group leaves. Everything happens all at once. And in the transition state, for a fleeting moment, this carbon is sp2 hybridized. And at that stage, it's perfectly lined up for the electron density in this p orbital to overlap with the electron density of the neighboring benzene ring. And that helps, okay? Because one of the golden rules, apart from Coulomb's law, is electrons want to spread out in space. Now, the last one that we did for allylic applies here too, and that's acidity, namely benzylic anions. Here again, the negative charge profits from delocalization. So the pKa of methylbenzene is rather low compared to the pKa of, say, methane. Okay? It's about 10 units lower, and it's completely comparable to the pKa of propene, okay? Which is about 40. This one is about 41. And the reason is that deprotonation generates a benzylic anion that can undergo delocalization, so you can get the allylic anion resonance stabilization, where you get allylic transposition. Negative charge moves here, and then again to here, and then again to here. And the way to deprotonate that guy, because while this is lower than 50, a pKa of 41 is still terrible, is to use a very strong base, butyl lithium, or alkyl lithium. Butyl lithium, as you remember, shows up because it's a cheap reagent that organic chemists use. But you could use methyl lithium if you want. So butyl lithium deprotonates and gets the corresponding benzyl lithium. And these guys react like ordinary alkyl lithium derivatives. They react with aldehydes and ketones and alkylating agents, as long as they don't undergo E2, okay, because this is a very strong base, and so on. Very similar to an allylic organometallic. Remember also, by the way, that of course you can make benzylic organometallics, benzyl lithium or benzyl grignard, from the corresponding halides, which you can make by radical halogenation at the benzylic position. So there are two ways of getting at this. So now we can also do specific benzylic oxidations and reductions because of the reactivity of the benzylic position. And the first reaction I'm going to describe is actually sort of a very rough reagent, potassium permanganate, which is sort of the manganese analog of sodium chromate. Except that it's much more reactive. It has a much higher oxidizing power. And that will take an alkyl benzene and take down the alkyl chain all the way to the corresponding carboxylic acid. Quite a remarkable reaction. Not often used, but sometimes it comes in handy if you have a cheap alkyl aromatic that comes from nature, from oil or something like that, and you want to make large quantities of a carboxylic acid. This is the cheapest way of doing it. So you just take down all the alkyl groups down to or take them up, depending on your point of view, to the corresponding carboxylic acid. So this also goes with sodium dichromate. But you need to beat on it a little more. I'm not going to show the mechanism of this, except that to give you some global big strokes type of explanation. These oxidizing agents are electron sinks. In other words, oxidizing agent is a species that absolutely loves to take electrons away. And for benzylic positions, what it does, it removes proton as a hydride, H-. So it takes the proton plus its electron pair, because the chromium, in the case of chromium-6, wants to be chromium-4. So it picks the two electrons to reduce itself, as it were. Okay? When you do that, you get a benzylic cation here. And that cation is immediately trapped to give the alcohol. And the alcohol, in the presence of either one of these oxidizing agents, we know it very well for chromium-6, of course, immediately oxidizes to the ketone. Okay? And you can actually stop here in the case of chromium-6. Does that look familiar? Yes. That's exactly the reaction that we used in order to convert an alkyl group derived from a Friedel-Crafts alkylation into an acyl group by oxidation with chromium-6. That is that process. Okay? And you can stop here. If you have a stronger oxidizing agent or you beat on it a little bit, this actually goes on. That is, the ketone is in equilibrium with the enol by the usual keto-enol equilibration, and then this double bond gets oxidized, not unlike osmium tetroxide. All these guys are very related. So two oxygens add across the double bond, and then eventually the whole thing falls apart to the carboxylic acid. We'll see a case where this is actually synthetically useful in a later chapter. So that rips out the whole side chain and oxidizes everything to the carboxylic acid. But you're not going to go through a detailed mechanism of that. But it gives you a feeling of how this goes, and why with chromium we can actually stop here and use that useful interconversion of alkyl to acyl, orthopolar director to meta director in an aromatic. One can also do benzylic oxidations, just like allylic specific oxidations with manganese dioxide. Same reagent does the same thing. So we'll specifically only oxidize the benzylic carbon. And so if you have a diol where one of them is benzylic, one OH is benzylic, the other one is normal, manganese dioxide will specifically only oxidize that in very high yield, very selectively, totally analogous to allylic. Okay? So again, benzylic, allylic, same thing. Okay? You're not learning anything new. Just apply it now, also extend it to the benzylic system. There's one special, well, not so special actually. There's a reaction that also works for allylics, but it has a drawback for allylics that I'll explain in a minute. And that is reduction of benzylic ethers. It's unique in the sense that this bond here is activated by the benzylic system, even on surfaces like palladium. And so when you treat this guy with hydrogen under typical hydrogenation conditions, or with palladium on carbon, which was one of our very first catalysts for hydrogenations of alkenes, then what happens is a so-called hydrogenolysis. That is, you cleave this bond and cap it off with a hydrogen. And this is a very successful method to protect and deprotect alcohols. Because notice, the other product here, apart from this guy, which you throw away, is an alcohol. And you can, of course, turn the alcohols into the corresponding benzylic ethers by simple Williamson ether synthesis. A benzylic halide and an alcohol, do an SN2 with a little base, and that gives the benzylic ether. And the fact that you can deprotect, whereas normally primary ethers or ethers are very hard to hydrolyze, with the exception of tertiary butyl, where you go to tertiary butyl cation. This is a perfect protection strategy for an alcohol, where the deprotecting step is not acidic, like in the tertiary butyl ether protection. It's neutral. So you can actually selectively protect a diol. One side is a T-butyl ether, one side is a benzylic ether, as a benzyl or phenyl methyl ether, and then selectively deprotect one over the other, because this guy is acid insensitive. It won't cleave with acid. Okay? It's also base insensitive, so you can also do Grignard reactions somewhere down the line. It's a perfect protecting group for an alcohol, and this is definitely something that will show up in the final exam in one of your strategies to build something complex. Okay, so now we'll talk a little bit in the remainder of this chapter about functional groups. So in this case, phenols. Phenols, remember, are enols. Okay? And the cute thing about them, and you may have already noticed that, is that they exist in the enol form because of aromaticity. So here, the keto-enol equilibrium is actually way to the right. Remember, for something like acetone, the ketone form and aldehydes, the ketone form was the more stable one. For acetone, the equilibrium with enol was 10 to the minus 5 or 6 or something like that, right? So that ring, 10 to the minus something. This equilibrium is 10 to the plus 13 to the right. And the reason is aromaticity, and you can accentuate that also with the OH donating electron density. We've done all of this in electrophilic aromatic substitution chemistry. And the naming of these, UPAC accepts the name phenol, so we don't call them benzenols, we call them phenols. And otherwise, everything's the same. The hydroxy function by definition is therefore on carbon 1, and so this guy would therefore be 4-methylphenol, and this guy would be 4-chloro-3-nitrophenol. A little reminder here, by the way, 4 is before 3, because these names are not numerical. In numerical order, they're in alphabetical order, C before N. And benzoic acid, carboxylic acid has precedence over the hydroxy, so now this would be a hydroxy benzoic acid, 3-hydroxybenzoic acid, and their diols and the like. Phenol ethers, they're named just like normal ethers. Normal ethers are named alkoxyalkanes, so they're named, the RO group is a substituent. It's not a functional group. Same thing for phenol ethers, this would be methoxybenzene. Okay? When this is a substituent, it's called phenoxy, which is a short term for phenyloxy. Okay? So phenoxy like methoxy and tertiary butoxy and so forth. Many, many natural products. I just picked 2. Some of them are quite interesting. This one, for example, is a phenol with a ketone at the end. Quite simple structure. It's the flavor of raspberries. So next time you eat raspberries, think phenol. This one, I love it very much. This one is capsaicin. This is the compound responsible for the hotness of hot peppers. And I happen to love hot food. I have a whole collection of hot sauces at home, which go by various exotic names like ass reaper and the like. And it's this compound that actually does it. Okay? Notice it's a phenol with an ether function, and it's also an amide, and it's got a double bond in the end. And the activity of this compound is actually quite remarkable. The hotness, which you feel, I mean, a lot of people experience it as pain. Okay? Depending on your level of masochism, it's either pain or pleasure. Okay? And I'm a high level of tolerance for this guy. It tricks and it activates a protein that is involved in activating your pain system. So it tricks your body into thinking that it should feel pain, when in fact there's no damage to your organs. Okay? You just apply this compound and it starts acting on your eventually your nervous system such that you think that there is something that's happening to you that should be painful, but in fact nothing is happening. Except when you take a lot of the stuff, you do actually get then blisters and stuff. But for the normal dose that people have, this is trickery. And part of that is used in medicinal applications. There are patches that you can apply for people who have chronic pain, where you actually use this compound, an 8% solution of this compound in a patch. You put it on, it burns a little bit at first, but then it goes away because it overstimulates this protein, as it were. It short circuits it, if you wish, and your pain goes away. So this is a very successful application to pain treatment. On that note, I'll see you on Thursday. Thank you.